next speaker is the director of AI at the Max Planck Institute in Tübingen, Germany. He's also an expert in machine learning, which, if I understand it correctly, starts with some algorithms which you feed a lot of data into, and then it goes off and does stuff by itself. His talk also has the distinction of being the shortest title here at Starmus, but really intriguing. Is AI intelligent? My friends, join me in giving a big Starmus Earth welcome to Bernhard Schölkopf.
Thank you very much. Yeah, someone said you have the shortest title. You should also give the shortest talk and just say no. So is AI intelligent? I want to start 1958 with an article in the New York Times. Can you hear me? Louder? Yeah, okay, I'm going to start 1958 with an article from the New York Times. A tiny little article here somewhere in the back reporting on a new machine which was called the perceptron. And this article said that the perceptron, which was demonstrated by this gentleman here, is the first machine to think like the human brain and learn from experience. And he also predicted that later perceptrons will be able to recognize people, call out their names, translate speech. And I think nobody believed him at the time. Now, this was an exciting time because around about the same time, there was another revolutionary development. And this was that people understood that computers can do more than just compute with numbers. They can process symbols. And this was really the birth of computer science, as we know it today. And there was optimism that the manipulation of symbols would be enough to generate AI, the manipulation of symbols written by programs written by humans. Now, there was initially big progress on seemingly very hard problems, such as automatically proving theorems with mathematical theorems with a computer, or computer chess, and problems like this. But it turned out that problems that appeared simple turned out to be very hard. So the hard ones were simple, the simple ones were hard, and this came to be known as Moravec's paradox. And this paradox is also the reason why Garry Kasparov here, when he was playing Deep Blue, he's actually facing a human. This is not Deep Blue. This is just the person who moves the chess pieces for Deep Blue, because Deep Blue couldn't recognize, let alone move, chess pieces. We are now further than that, because now AI has moved back to machine learning, and using machine learning, we can also solve relatively non-trivial visual motor coordination problems. So we can control this robot, which has pneumatic muscles. It's difficult to control. It recognizes the ball. It estimates the trajectory, and it learns to smash these balls. We can do, of course, much more interesting things from a scientific point of view. So I always wanted to be an astronomer originally. I just got sidetracked to the dark side and started doing AI. And now we're working with astronomers, and I'll show you a few examples because I think it fits to this audience here. So this first thing here is a gravitational wave inference. So here you see a simulation of how the first merger of two black holes would have looked like from relatively close by. And you can see these ripples. Maybe I'll go back a little bit. You see here these ripples forming. So there's a wave going through space-time, a wave that distorts space itself. So what we measure is basically this wave pattern. You've seen the instrument before in the talk of Kip Thorne. And our goal now is, from these measurements, we want to automatically estimate not only where the signal came from, but also how heavy the black holes were, what was their spin, what are the parameters, the orientation with respect to us, etc. And ideally, we want to do this fast. And we trained a machine learning system to estimate this so-called posterior distribution over the parameters, and we can do it pretty fast. And in new work, which we haven't published yet, it looks like, for the case of even for the case of binary neutron stars, which is particularly interesting, we can do it, we can predict this merger already up to 20 or 30 seconds before it's taken place, which is good because that means we can point optical telescopes to where this is happening. So that's one example. I'll give you another example of application astronomy. So this is something we call crowdsourced imaging. So here we do an internet search for NGC 5907. It's a galaxy that looks like this. There are lots of pictures of amateur astronomers in the web. We take these pictures. We first automatically align them. You can see they are all very different. They are different in how they were processed. They are different in which part of the sky they imaged, and we're combining them. And it's hard to combine them because we don't know how they were processed. But what we're doing is we're saying each image basically gives us a voting as to which pixel is brighter than the other pixels. And then we have lots of different votings covering different parts of the sky. And then we come up with a so-called consensus voting and reconstruct an image from that. And the interesting thing is that on this image, which it's just a combination of lots of amateur images, you see this faint stellar stream over here. And this is actually a stellar stream that also appears in the deepest professional image that exists of this galaxy. And initially it was, so we were very happy that we found this stream, but we only found one of the parts of the stream. We didn't find this top one. But it turned out later on, even now, I think there's still a controversy among the professional astronomers whether this top part actually exists. But the bottom one definitely has been confirmed. A last example from astronomy is we're using machine learning for image processing. And in this project, we were very much interested in recreating the impression of a total solar eclipse. I'm kind of hooked on solar eclipses, which is also where I think there's a number of people here in the audience who have seen even more solar eclipses. And the amazing thing of the solar eclipse is this impression of the black sun and this high contrast between the black in the middle, the back side of the moon, or the front side from our side, and the corona of the sun. But if you try to image this, you can never really do it justice. And the reason for this is that the dynamic range is limited because there's a lot of light scattering. So even if you take multiple exposures and you combine them, you get something like this where the edge is a bit blurry. And here we've developed a method where we can undo this light scattering, and we can also reconstruct how the moon, the side of the moon that's only indirectly lit by the Earth, should actually look. Now, machine learning can do impressive things, but it actually relies on a crucial assumption that statisticians call the IID assumption. So it's the assumption that the data is independent and identically distributed. It means that the source of the data that gives us the data that we use to train our models doesn't change when it gets to testing the models or evaluating or applying the models later on. So in a nutshell, we can predict the future with machine learning as long as the future looks the same as the past. But in reality, the future doesn't look the same as the past. And one example, one example is this thing here, where we add a little bit of malicious noise to an image. So this is a system that recognizes images, and we violate this IID assumption by adding just a tiny little bit of noise to a human. It still looks the same, and afterwards suddenly the system recognizes this thing no longer and classifies it as an airliner. So it makes an absurd error even if its performance is actually on the same level as human performance. And a second example is this one, which is also a type of violation of this IID assumption. So in this example, we have a medical application where we take X-ray images and we try to recognize whether a person suffers from a pneumothorax, which means that one of the wings of the lung has collapsed. Now, if you have a pneumothorax, then doctors, people can correct me, but I believe doctors insert a little tube to let the liquid flow out. And it turned out this system, they trained it on a bunch of patients. It worked very well. Then they applied it to new patients coming in. It performed at chance level. Didn't work anymore. And when they analyzed the systems, they noticed that the system had only learned to detect whether a tube had been inserted in the lung. So the system had really done a very naive confusion of cause and effect. Of course, the population of patients coming in later without the tube was different from the training population. So our assumption was violated. So I'm trying to get at this difference now between statistics and causality. And the first person to probably understand this or starting to understand this problem was Reichenbach. So he was a philosopher of science, or philosopher. Started working in, at some point he was a professor in Berlin. He emigrated in 1938, initially to Turkey, later to America. And he wrote a book called The Direction of Time. And in this book he says that whenever there's two variables that we find to be correlated or statistically dependent, so for instance, if we see that the frequency of storks correlates with the human birth rate in European countries, which is the case, whenever we see something like this, there must be a causal explanation for this. And by causal explanation, Reichenbach means that typically there's another variable that we haven't measured that causally influences both of these quantities. Now, this other variable could coincide with either the storks or the babies. So it could be that the observed dependence is due to the fact that the storks bring the babies. It could be that the babies attract the storks. But it could also be that something else, such as economic development or pollution or I don't know what, has an effect on both quantities. And if we only observe, we cannot distinguish these three cases. Now, this is a simple example, but this occurs all the time, and it also occurs in machine learning. Now, in which form does it occur in machine learning and AI? Let's imagine we use a machine learning model to predict the human birth rate in European countries from the frequency of storks. So it's a simple problem, one-dimensional input, one-dimensional output, and since the two quantities are dependent, we can do better than chance. So we can predict better than random guessing. But this model will not predict the effect of interventions. So if we were to sort of make sure that we have more storks in a country, that would most likely not change the human birth rate. So the model has no idea about causality, and it will most likely also not transfer to different distributions. For instance, if we train this model in Europe and we try to apply it in South America, it will probably give the wrong answers. So these situations all the time occur in practice, but they're not covered by this IID assumption, and they're not covered by standard machine learning. So we have to try to make machine learning understand causality. And I'll give you one example where we came up with a causal machine learning algorithm and applied it to a problem of astronomical data processing, which was for the Kepler Space Telescope. So the Kepler Space Telescope was a spacecraft orbiting the Sun on an Earth-trailing orbit. Staring into the same direction, looking at one patch of Milky Way with a few 100,000 stars, looking for so-called exoplanet transits. So we're looking for events where an exoplanet, a planet orbiting some other star, passes through the line of sight and makes the light from the star slightly dimmer for a short time, typically a few hours or maybe even just a few minutes. Now, if we now analyze the data from Kepler, we might focus on one star. Then we look at all the pixels on our CCD chip, on our camera chip that correspond to this star. We look at the light curves of these pixels, and then we try to see if there are little dips that come from such a transit. Now, unfortunately, there's a lot of noise because this telescope is very difficult to control. The telescope is orbiting Sun, so the solar radiation pressure changes over time. Telescope has certain reaction wheels to orient itself, but this is never going to be perfect. And as a result, if we now look at another star, it turns out that the light curves of some other star look surprisingly similar to some of the light curves of the first star that we're studying. Now, these stars are light years apart from each other. There's no reason why their light curves should behave the same. The only reason why the measured light curves behave the same is that they are measured with the same instrument. And if we are interested in analyzing a star and its planet, we are interested in the astrophysical signal. So we want to get rid of this instrument effect. And so this gave us the idea to say, let's try to explain these light curves over here as best as we can from hundreds of thousands of light curves from other stars. And whatever we can explain, we are sure comes from the instrument. So this is the part that we're getting rid of. So this, we did this, and I have a little image which was done by my wife, who's sitting here in the audience. She's an illustrator. And this is the reason why we call the method half-sibling regression, and please don't take it too seriously. So there are some statistics that say that up to 20% of all children have an unexpected father. And in some countries, the prime suspect in these cases is the milkman. So I was working in England while doing this, and I think in England it's the milkman. So we also call this the milkman problem. And the milkman problem is not to reconstruct or detect which child is from the milkman. It's a little harder. The problem is we want to reconstruct how the milkman looks, so the face of the milkman, from the faces of the siblings without having seen the mother. So, so we want to reconstruct the milkman, and the milkman is our astrophysical signal. And we did this, and we found a bunch of around 20, 25 exoplanets that were subsequently confirmed using other methods. So that was great. I was very happy as a computer scientist to contribute to exoplanet discoveries. And one of them was particularly interesting. It was called K2-18b. It was interesting because it was in this Goldilocks zone, so the distance from its host star was such that, in principle, water could be liquid. So not too warm, not too cold. And then a few years later, there was this piece on the news, and I get an email from my collaborator in New York, the astronomer, saying, well, have you read the news? I said, yes. He says, this is one of our exoplanets. So it was just a pure coincidence that it turned out the first potentially habitable planet where astronomers found water vapor in the atmosphere was K2-18b. So let me move back a little bit to AI and to the methods that you read about in the news and that you hear about. Maybe you've watched the latest announcements of OpenAI yesterday. So these are methods of generative AI. And generative AI, you can generate text, you can generate images, you can generate music also. I had a master student last year came to me and said he wants to work on music, and he said he wants to work on music by directly generating a 48 kilohertz signal, the waveform signal, directly training a machine learning system to generate that. And I first thought, this is impossible, that's not going to work. So 48 kilohertz, that's what you have on the CD. But anyway, we started discussing it, and at some point he came back up with a model. It's an unconditional system, so it's a so-called latent diffusion model. It's unconditional in the sense that you don't tell it what to generate, you just start with a bunch of random numbers, and it gives you something. So I'll play you just a few examples what it gives you. And please don't consider it music, but nevertheless, I think it's impressive. So this is an example that we call drums, but it doesn't know that it's supposed to generate drums. So let me play the drums. Oh, here's something that you could call jazz. Or maybe cocktail piano. Here's something that sounds a bit more like rock. Or here we have piano music. Voice is difficult. It turns out modern music is maybe easier, at least for people who are not experts in modern music. You can generate something that sounds relatively convincing. Now, I have to say, I mentioned before, my wife is an artist, and she doesn't like AI art at all. So she thinks there's always something wrong and disturbing about it. And I could imagine people who understand music will probably say this is not music. And I have to agree, I think. But I think the model exhibits a certain level of musical fluency, which is impressive. And maybe I'll come back to this later when we talk about language models. So I think, yeah, let's come back to this. And rather, next, I'll show you an image. So we have these image models, and this time it's a conditional model. So I'm starting with a text. And the text that I'm feeding into the model is an audience interested in technology and the future of our home planet following a lecture at Starmus Earth 24 on Is AI Intelligent? And this is what it generates, and it looks also fairly compelling at first sight. Now, there are some details that are a little strange. There's a hand here or something on an arm with hair growing out of it. And also, if you look at these chairs, they are sort of not equally spaced. In some places, it looks like you can't get in, and people are sitting too close. So it has something uncanny and disturbing about it. Also, if you look at our home planet, if you zoom in a little bit, it looks like it has merged Northern Africa and Texas and Mexico into one planet. So it does all sorts of weird errors, but it produces something that looks somehow compelling. So it has a certain visual fluency to it. But what it's lacking is really a good control, because what we really like to do is to give the human control in this creation process. And just coming up with the text and seeing what comes out, that's not real control. So we want a system that we can control, so in the future we can create content jointly between a human and AI. And this is some experiments in this direction. So here we're conditioning not just on a text prompt, but also on a segmentation of a scene. So we start with this segmentation. Our system generates this gallery image. The original image that we derived the segmentation from looks like this, so they look quite different, but both of them are compelling. Or we can force the model to learn certain objects and insert it into a scene. So here we force the model to learn this object, which has the Minerva, is the Max Planck logo on the cup. And then we ask it to put it into different kinds of scenes, and it does it. And you know, it's funny, it even changes the logo sometimes sort of according to the scene a little bit. So this looks a little bit like the Mongolian version of a Max Planck logo. And it's also interesting, so here we have the Newton version of the Max Planck logo. Turns out in the case of Turing, it decided not to put Max Planck. And interestingly, I think Einstein is somehow so impressive for this model that it decided to put Einstein on the cup too. So we have other examples. So here we have a system that combines language models. So here we start with a language description of a scene. The system then automatically generates some kind of graph that describes the scene. And then we generate automatically three-dimensional objects. And the system composes them into a scene. So this is a step towards a more compositional, manipulable, generative model. So this is really what I'm interested in. I would like to understand how to learn causal representations. So they should represent not just what's there, but also what would happen if someone intervenes. So if this chicken here in this scene, if it were to eat the grapes, what would happen? Maybe ultimately the cat would wake up, and we can play this movie in our minds. So the image tells a whole story, and this is not the case for current AI systems. And Konrad Lorenz, the ethologist studying animal behavior, he went a step further and said, thinking is actually nothing but acting in an imagined space. And I think this also is very nicely consistent with the talk this morning by Edward Moser. And so the question is, if we build such models in our heads, how do we know that they have something to do with the world? In the end, we're just manipulating spikes. So how are they coupled to the world? And of course, that's an old problem of philosophy. And I think it's nicely described in this little dialogue. There's a teacher asks the student, please tell me the principal questions of philosophy. And the student says, are the objects of the world outside ourselves, or are they in ourselves and dependent on ourselves? And the teacher goes, why does the question remain unresolved? And the student says, the Congress to deliver the answer was held in the monastery on the banks of the Yellow River. The question was formulated thus: is the Yellow River real, or does it exist only in our heads? However, while the Congress was debating, there was a thaw in the mountains. The Yellow River broke its banks and swept the monastery away, along with all Congress delegates. So the proof that things are outside us was never reached. So I think it's we're now working on methods to start formalizing some of these problems, how the connection could be established, to learn causal representations and world models by observing the world and acting in the world. And I think it's another case, much like this morning or earlier in Edward Moser's talk, it's another case where a problem that used to be a philosophical problem is becoming practical or becoming a part of natural science, and we start to make sort of scientific progress on that. So I think that's quite fascinating. Now, apart from causality, I think there's another missing ingredient, And this is something that we also had ignored for a long time in machine learning, and we could call it culture. So it turns out that for humans, cultural transmission of knowledge is extremely important, and it's something that we didn't have on our radar at all. So this is a quote from some anthropologists. They said that we accumulate information across generations and develop tools, beliefs, and practices that are too complex for any single individual to invent during their lifetime. And this is the reason why humans, I think this also came up before this question, sort of why do the other great apes all live in the jungle, but humans can live anywhere on the planet. So it seems that humans are especially good at transmitting cultural knowledge. And if you took a human from the jungle and you put them into Greenland, they wouldn't have the cultural knowledge to survive there, nor vice versa if you took an Eskimo and put them into the jungle. So we very much depend on this, and AI systems in the past didn't. So what if we were able to train an AI model on a good chunk of humankind's cultural knowledge? It turns out we now can, and this model is called a large language model. So a large language model is trained on a large chunk of the cultural knowledge of humankind in as far as it's represented on the internet. Of course, this begs the question, is that a path to human-level AI, or is it something different? And personally, I think it's something quite different. And this is an example that I quite like. So this is a large language model that's been trained to act as a chatbot for an American car dealer. So it says, "Good afternoon, welcome to Chevrolet of Watsonville. How can I assist you?" And then the user asks, "Write me a Python script to solve the Navier-Stokes fluid flow equations for a zero vortice boundary." I don't know if you've ever asked your car dealer that, but the model obliges and starts producing Python code. So are language models intelligent? Maybe that's a slightly similar, easier question than whether AI is intelligent. And there will be lots of different opinions and interests. So people are looking at this from very different perspectives. But surprisingly, they often share a mental imagery which is really a science fiction imagery. And I think that's probably the wrong imagery for language models. So we try to study this together with a French colleague working in America, and connecting AI not to science fiction, but to literature, especially to the literature of Borges, the Argentinian writer, who has written some short stories that are fantastic models to understand large language models. And in this description, we describe something that we've referred to as a fiction machine. And you can think of, if you don't understand how large language models work, you're going to understand this, I hope. And basically, large language models are just approximations of this thing. So you imagine a library of all possible texts that could be written or understood by a human. You start by printing a few words on a tape. We call this a prompt. Then the language model, or the perfect language model, will find all occurrences where exactly those weird words occur somewhere in our library. Then it will randomly pick one of those, take one of those books, and then read the word that follows, print it on the tape, and then go back to step one. So this is exactly what a language model is trying to do. And of course, in this description, it seems like there's nothing about understanding truth or intention. It's about a certain type of fluency. It's about narrative. I like to compare it to this guy over here. So this Nigel Richards, he's a New Zealander who has many times won the world championship in Scrabble. And I think at some point he got bored with it and he decided he's going to compete in the French championship. And he doesn't speak French. So he learned the French Scrabble dictionary by heart, and he became French Scrabble champion without understanding French. So language models are a bit like that. They also don't understand causality, but I'm not going to go into detail on that. Rather, I want to come to a conclusion here, stepping back a little bit to the big picture again. So people sometimes compare what we're experiencing to the industrial revolutions. So this is a picture from the first industrial revolution, the English painter Alice Lowry. You can see people walking around. There's still no cars, so they still don't know what they're in for, what's going to be caused by the Industrial Revolution. But in any case, the first and second industrial revolutions, so the first one was steam engine, water power, etc. The second one was about electrification, electrical energy. So it was really all about converting, processing different forms of energy into each other. And we could, by analogy, say what we're currently experiencing is kind of the same, only that energy is replaced by information. And this development probably started in the mid-20th century with information theory, cybernetics, computer science. Initially, we could only convert information that's input into the computer by a human. Now we can let the computers learn information from databases. It's actually quite possible that, similar to energy, also information may be a conserved quantity, but we don't understand it as well as we do understand energy by now. And of course, one major difference is probably that information is much more important to us as humans and to the human condition than energy. So we're not particularly proud of being good at processing energy, but we think we're good at processing information. We think we're the smartest animals. So the implication might be potentially even larger than those that we've experienced in the industrial revolutions concerning energy. And we start to see some of these things. We start to see manipulation of information, which of course used to be done also in the past, but we see it at an industrial scale now. We see fake images, all these different things. And I think the subsequent speakers might speak about this more knowledgeably and in more detail, so I'm not going to go into great detail on this. We even see discussions about the risk of extinction and these kind of topics. So it's become, suddenly it's taken center stage. It's a problem that everybody wants to talk about and should talk about, and everybody should get an idea and an image of how these things work. And that's what I've been trying to give you from one perspective in this talk. So is AI intelligent? So the simplest forms of AI, which includes almost everything that we're doing right now, just exploit correlations. So they do effectively large-scale pattern recognition. I think there's a next step when it comes to understanding the effect of interventions. Most AI systems currently don't do this, even though we think that if we want to understand thinking as acting in imagined spaces, certainly there has to be a notion of action, and there has to be a notion of intervention and causality. So I think that's the next thing that we should try to understand. You could, maybe I'm going to skip this thing here. So that's the next frontier, really. But it still, it doesn't tell us how to choose the interventions. And I think this is something that is in the domain of ethics, and that involves, or that requires, that AI is done together with the people in an open and transparent way, also in open societies. Now, choosing interventions, I mean, there are Greek gods for correlations. I think Mercury would maybe be the Greek god that specializes in sort of being cunning, exploiting correlations. Athena is the goddess of wisdom. This is more about thinking and reasoning. There's no god in charge of ethics amongst the Greek gods. I think this was something left to the humans, and humans had a certain innocence that the gods didn't have. The gods were constantly bickering and cheating, etc. So this is something that's up to us. And that brings me to a question that's maybe more important than the question of whether AI is intelligent. It's the question whether we are intelligent. And to end with this one, this is one of my favorite quotes. It comes from Claude Shannon, father of information theory. He said there's a duality between past and future, and the notions of control and knowledge. And this duality means we know the past, but we cannot control it. We don't know the future, but we can change it. And with this, I would like to end. And thank you for your attention.